Здравствуйте. Как-то мне вас не слышно. Может, остальным слышно?
Сейчас слышно?
О, да, теперь слышно. Здравствуйте.
Так, понял, в чем дело. Yes. Раз, два, три. Ага, все.
Раз, два, три. Слышно что-нибудь?
Да, да, все слышно. Раз, два, три слышно.
Да. Хорошо.
Ну, вот видите, кто у меня вместо кота теперь?
Ну, нет, конечно, это самое. Кот тоже был хороший, но это даже интереснее. So as usual, I encourage people to switch on the cameras so the speaker can see the disapproval faces and correct something. Sasha, can you hear us? Oh, hello. I see you are in Moscow back
Hello, yes.
outside the icosahedron.
Yeah. Yeah. Yeah, now
They
the room.
let you in.
In disguise. He is in disguise of Ольга Еремина.
Oh,
Okay,
sorry.
you
Yeah,
know.
yeah.
No, but we trust you
Yeah.
anyway.
Can change my name.
Yeah, Danya, there is a plan that next time maybe Kolya will explain about cats and ants again. So I wrote this to
Yes,
your
I saw
students.
that.
Yeah, so if they are available, that's great. If not, we can he can do it another time. Just because once they asked how to explain it easily, and Kolya claims that he knows how to do it. I'm not sure, but still, I think it's better than
Okay.
it was before.
Okay, I will ask them.
Yeah. Yeah, and thanks for the 010106 program. It's a bit stupid, but still.
Which is now another number.
It doesn't exist 010106 010106
No,
agents.
the classification has been changed.
It is now
somehow.
115, which is 010106 and 010109 together.
Okay, so you now need to pass the exam not only in analytical number theory, and algebra, but also something else.
Well,
Wait, what are you talking about? It's a specialization like this
Yeah.
mathematical.
So, for example,
Logic
your
algebra.
thesis was which number?
I think 010106. Mathematical logic, algebra, and number theory. Everything, you know.
Yeah. And do you know, for example, have you when you passed exam, did you learn why the prime numbers are distributed as
No,
they are?
I was learning algebra and logic, but number theory was I could choose two
Yeah.
out of three.
Oh, it's kind of cheating. And but for example, you know what is Wedderburn theorem in
No,
algebra?
no, I don't remember this name. So I don't know.
Okay.
Sasha, it's time to start the talk, I guess.
Yeah. Okay.
So Ivan, you can start.
Hello, can you hear me?
Yeah. Perfectly.
So I'll try to share my screen now then. Can you see my screen?
Yeah.
So I decided to make a small presentation and to leave it with proof so we don't lose track on the topic because it is a bit abstract. So sometimes one easily gets lost in the details and forgets what we're actually proving or why were we doing this stuff. So the topic for today's talks are algebraic matching algorithms. We'll cover the most important ones, why are they important, and recent developments in that field. Yes, so
Yeah.
we'll start with some background for people who are already less familiar with matchings. So in a graph, a matching is a way to pair the vertices according to the edges. So it's a subset of edges such that every vertex has at least appears at most once in a matching. Now we distinguish between maximal matchings and perfect matchings, where a maximal matching is the largest matching you can find in a graph, and a perfect matching is a matching which covers every node. So here on the figure, we have an example of a maximal but not perfect matching, because if you look in this graph, you can easily see that you cannot find a matching of size larger than 3. Nevertheless, a perfect matching would pair all the vertices, so we would need a matching of size 4 for it to be perfect.
Yeah, so actually you can also define another different notion of maximal matching, which cannot be extended. But here you just speak about matching of maximal size. Yeah.
Yes, and they are equivalent, but
not equivalent. If maybe you have a matching which cannot be, no edge can be added, but still a bigger one can be found. So
yeah,
it's not the maximal in the sense of partial order, but okay.
Yeah. So there are two notions of maximum, and we use the largest one. So in general, finding maximal matchings is as hard as finding perfect matchings, and finding perfect matchings is as hard as deciding whether a perfect matching exists. Now there are reductions, so you can reduce the problem of finding a maximal matching to finding a perfect matching, and deciding whether a perfect matching you can reduce to a problem of finding perfect matching you can reduce to a problem of deciding whether a perfect matching exists. Now we won't show these reductions right now. When we will need them on the way, we will construct them. But for now, it's just good to know that these are all free.
But who knows them by example? But just let's who understands why they are these problems are in P in the same time? Are there anyone advanced enough in algorithms to see why it's so equivalent?
Which two?
No, just okay. Do you know at least two of them are equivalent, Sasha?
Yeah? Which two? I don't understand.
No, there are 3. There is a problem of finding the maximal matching, finding the perfect matching, and deciding whether perfect matching exists. maximal size matching, let's say, because just maximal matching is obvious, but just maximal size matching.
What they
Do you
mean,
under-
whether the maximal size matching exists.
No, of course, maximal size matching always exists, but there are three problems: find a maximal size matching, find a perfect matching.
Deciding whether a perfect matching exists.
Yeah, it's the third problem.
Okay.
So do you
Well, I don't
know?
know. Let's what is obvious. If we can find maximal matching, we can find perfect
Of
matching.
course, we can
if it
find
exists.
whether a perfect matching exists, but the question is how to switch from deciding whether a perfect matching exists to finding the perfect matching, and how
Or
to
finding
switch
the
from,
maximal matching.
or from finding the perfect matching, how to switch to finding the maximal one.
Yeah, so I
Bruno
think-
knows this.
Oh, yeah,
Why?
okay. Yeah,
I
so-
don't understand. All these problems are in P. So there are obvious
Okay,
P
but they are not
reductions.
obviously in P, but there are some
Do
obvious
you mean
reductions.
log space reductions or what?
No. I just mean obvious reductions.
So okay, so you say that whether if, for example, if I can decide whether a perfect matching exists, how to, let's say, find the perfect matching?
Yeah.
I guess
How
try
to-
all ages
yes.
And
So-
check whether
and
matching exists for
So
the
remove
rest.
the edges.
if you remove this edge and the perfect matching exists without these two nodes, then you proceed, no? Or
Yeah.
it's too bad?
So one reduction is clear, and another reduction.
Wait.
does
I
anyone-
don't understand. But is it like factorials? Wait, what I'm actually doing?
So you
Maybe it's a
iterate
bad
over
reduction.
No,
all
it's
the
just a
edges.
polynomial on the number of edges, so it's okay.
Yeah, it's
Ah,
we just,
yeah. We don't have
yeah.
to check all the others. So once we found that
Yeah.
for some edge, if I remove it, then the perfect matching exists. Then I
Yeah.
just repeat it for a smaller graph, and it's polynomial. Yeah.
Yeah. Okay, anyone
And-
knows any other reduction?
No.
No, it's okay. If
But
not, then we continue and see. So just at least to see what is obvious and what is not.
Okay. So
Okay.
we have algorithms defining all these matchings, which are polynomial, and some of them are even linear in some cases. But all of them cannot be parallelized, meaning that we cannot run these algorithms in parallel. They have a long path dependency in the computation. So how do we solve this problem? We solve this problem with algebraic matching algorithms. And we start with randomized ones. And consider first the simplest case, which maybe most of you know, are the bipartite graphs. So the idea is if you have a bipartite graph, you construct an adjacency matrix for this bipartite graph where you assign a new variable to each edge. So as in this case, you can see you have a graph and a corresponding adjacency matrix, and every edge has a different variable assigned to it. Now, if we consider a non-zero permutation of this matrix, or a permutation which does not contain a zero, then this permutation will correspond to a perfect matching in the original graph, because it would be exactly an edge from each vertex taken exactly once. That means that if a perfect matching exists, we could the determinant of this matrix A should be non-zero, because the determinant will contain all permutations, meaning also all non-zero permutations. So there is at least one non-zero permutation. We're all good.
The determinant as a polynomial in the variables.
Yes. So the determinant with these unknowns. So how do we actually verify? Obviously, we cannot compute the determinant of this matrix because it has unknowns. That means that we have to rely on randomization.
Oh, we can compute it, but it's exponentially long. It's a
Yeah, I
polynomial.
mean, we need
Yeah,
exponential
yeah,
time
yeah.
to compute.
Yeah.
That's true. But normal determinant algorithms which run in polynomial time, they obviously don't work here. That means we will rely on this following very important result from the randomization theory, which is the Schwarz-Zippel lemma, which says that if we have a polynomial which is non-zero of maximal degree d over some field, and we consider an arbitrary subset of the field, and we choose a random assignment for each variable over this subset, then the probability that the polynomial under this random assignment will be 0 is less than the degree of a polynomial divided by the size of the set. Which means if we take the set of size 2d, for example, from natural numbers even, because in our case, x1 and xn can be variables over arbitrary field, we'll have a one with a chance of at least 50%, we will notice if our polynomial is 0 or non-zero. That means we have already, by just doing one assignment to the variables of x1 of the variables to the edges, Monte Carlo one-sided algorithm with a mistake probability of less than half. And of course, if you repeat it, then you can get your success probability to 99.999.
Technically, if you deal with natural numbers, then you can have big numbers. So it's not that obvious that you can do it in polynomial time.
But you can select a subset of the first 2D natural numbers, so like from 1 to 2D, and then just use this
powers
subset.
are in unary or in binary.
Sorry?
So in this polynomial,
No, if you start to computing a determinant, you get some rational numbers, and who knows what size of they have.
But it's exponential because
you start with small numbers.
We have
but
n
then
multiplication summed over.
No, actually, I guess it should not be exponential because you have exponential. Actually, the answer should be polynomial, but you need to deal what kind of the numerator and denominators you have. So there is a bit of
yeah. So there exists proof how to do compute determinant in
Why do you need rational numbers? If you are interested in matching in graphs, you can substitute integers.
No, but when you compute the determinant of an integer matrix, it's not completely obvious that this polynomial.
Why not?
Yeah.
No, how do you do this? If you do it by Gauss elimination,
no. There are polynomial circuits without divisions, computing determinant.
No, but it's not obvious.
Yeah, it's not obvious. Okay.
Okay, so no, actually, it's just if you need just this result, it's better to.
But actually, there is another way. You can compute determinant modulo primes.
Yeah, you either can compute determinant modulo
primes,
or just take the finite field modulo some prime in the beginning.
Yeah.
So that's why we're considering an arbitrary finite field, and this lemma holds in all finite fields. That means the easiest way is to take a finite field and compute the determinant there, and don't think about any problems. So with this way, we already solved the problem for bipartite graphs, because what we just need to do is put in random numbers in this matrix and compute a determinant, 10 times, and we can already be pretty much sure whether perfect matching exists or not. So now we extend this approach to general graphs.
Yeah, by the way, who knew this randomized algorithm in advance? It's probably many of us heard this about. So
why are you asking that? To just embarrass people who didn't know that?
No, just to understand, maybe it deserves more.
I didn't know that, for example.
Okay, so no, embarrass you is always a good idea. So indeed we have some achievement, but
at least I understood. Yeah,
but at least you learned something from the talk, which is great.
Yeah.
Okay.
So now we move to the general graph algorithm, which is a bit still pretty easy, but a bit more complicated than the bipartite one. And the idea is that instead of the bipartite adjacency matrix, which we considered last time, we considered a TUTS, the so-called TUTS matrix for the graph. Now, what the TUTS matrix does, it does not just assign a new variable to each edge. So first, what it does, it splits each edge into two. So as you can see here in the graph, we had an undirected graph and we got a directed graph, where each edge was replaced by two edges pointing in opposite directions. And then the one pointing from a smaller number to a larger number got a new variable, and its counterpart got the same variable negated. And this was done for all the edges. And for this graph, we just can consider the standard adjacency matrix. And this adjacency matrix is called the TUTS matrix.
More, just in other words, for an undirected graph, we have a symmetric adjacency matrix. So we have pairs of ones on both sides, symmetrical points. And then one is replaced by xij, and another is replaced not by xji as before, but minus xij. This is the thing.
Yeah, you can say it this way. And as you can see, because of this construction, the matrix is no longer symmetric, but skew-symmetric, meaning if we flip it, we get the negation. And to this new graph, which is the directed graph corresponding to our original graph, we will denote for the future the graph G star. So now we noticed that previously we had equivalence that for every non-zero permutation in A, our adjacency matrix, we had a perfect matching in our original graph. But now, because now permutations no longer correspond to perfect matchings, what they correspond to are one regular subgraphs of this directed graph G star, because every time in a matrix where we take an element from each row and each column, it essentially assigns every node an in degree and an out degree of 1. That means every permutation in A or in the determinant of A will be some one regular subgraph of G star. And now there is a theorem, which we're going to prove now, which says that a graph G has at least one perfect matching if and only if the polynomial is non-zero under this TUTS matrix. So essentially it says that even though we don't have the perfect matching correspondence anymore, and only the one regular subgraph correspondence, we can still infer the existence of a perfect matching just by looking at these one regular subgraphs. So now we make a proof. So as said, we start that every permutation is a one regular subgraph. Now, how do one regular graphs look? One regular directed graphs look? Well, these are just collections of circles. Obviously directed. This could be this one regular subgraph of G. And obviously these edges, they correspond to the monoms that we had in our determinant in the way that, let's number these nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we would have here x12, x23, x34, x45, x56, and minus x16 due to the property of the TUTS matrix. And the same we have here, so x78, x89, and minus x79. And this is a product, so we have this product in our determinant, so we have the determinant of A, which is a large sum of many things, and then we have this some sign function of this permutation multiplied with this polynomial, so it would be something like x12 times x23 times minus x79. And now what can we see? So first, let's consider the case where our case 1, where this one regular subgraph contains at least one odd cycle. Well, if it contains at least one odd cycle corresponding to some permutation, there is another permutation where this odd cycle is flipped.
Wait a second, the letters are very small. One even cycle, what is written?
It's written odd, but actually, in fact,
odd
if you can
cycle.
rotate the remarkable in a portrait mode, maybe we can see it better. But now
Right.
indeed the letters are very small.
Okay.
Landscape, sorry.
That's right.
Now it's better. Now one odd cycle.
So does this work?
Yeah, we see
Yeah,
now
it's better.
better, but of course we see only the first half. But
Yeah. There's okay. So now we consider case 1 on the next same page. If
We
it
are
contains
moving
at
it
least,
in which direction, actually? I don't understand. So we're in both directions simultaneously.
so the theorem. So now first of all we're doing the other direction. So maybe it's good to say the point.
So in the end, we want to show that all the things that correspond to these one regular subgraphs that are not matchings will catch perfect matchings will cancel out. That's the idea.
Yes, that's the
And
idea.
matchings won't cancel out. That's right.
Right, that's the general idea. So we're first doing this direction because this is the harder direction. And then we just do the simple direction afterwards. So case 1 is when we contain at least one odd cycle. So what do? Find the smallest cycle. So it's in subgraph of G, let's call it GS. Find smallest cycle, smallest odd cycle in GS, where smallest means contains vertex with the smallest number. So in our case here, that would be this one, because we only have one odd cycle. And what do? We flip it. So we consider a different subgraph, which just has this odd cycle flipped. And this odd cycle is now looking backwards. And this one didn't change, so I don't have to draw it in a detail. Now we look again at the monomial corresponding to this subgraph G, call it GS prime, in the determinant. Now obviously the only thing that has changed is the orientation of edges in one odd cycle. So the orientation of odd number of edges has changed, meaning the monomial here is the same monomial from before. So this one, let's call it, I don't know, mx1, 2, 10.
Permutation has the same parity because it has the same number of cycles. So this doesn't create problem.
The determinant of A will contain the same term, and obviously, yeah, the sign function, which we have here before the monomial, is unaffected because we have the same number of cycles in the permutation. So that means that the determinant will contain exactly the same term with a minus sign, which means that if we actually compute the determinant, it cancels out with the previous one. And we have a bijection rotating the smallest odd cycle. So that means determinant will contain only subgraphs with even cycles. If it does contain anything.
But
So
when do
let's
we
look-
use when do we use that the cycle is smallest? Just if we take any cycle and then they cancel each other.
Yeah, the problem is we need a bijection. So we need a term which cancels exactly one other term. If you just use some other term, I could maybe claim, well, this monomial, if we invert this cycle, this one already was used.
Ah,
to
yeah,
cancel out
you
a
need to
different
pair
term.
them using the
Yes.
same cycle. Yeah.
Yeah, so we need to
It
pair
should be
them,
like
so-
lexicographic first cycle if we ignore the signs or something.
No, actually, all
Yeah,
the
exactly.
commutation are specified.
Actually, there are possibly several cycles of the minimal size. So
Of
we
minimal
need
size.
something lexicographic order or something
They
like
take
this.
they take the smallest vertex, but actually it's not really important because all the cycles are splitted in classes depending on what are the cycles. So you have the non-oriented cycles and you have two orientations for each of them. And so if you split first, you consider all group of non-oriental cycles with all possible orientations, any odd cycle makes a way to cancel them all, because they you can do it using any of them, but still okay.
Yeah, that obviously works, but if you have it explicitly, it might be easier to follow. So now case 2, we only contain only even cycles in GS. Now, using the same argument, if we flip any even cycle, actually the sign of the monomial doesn't change. So if we only have like even cycles in our determinant, something like this. Rotating it or flipping it will not cancel it out because we're flipping an even number of edges. That means all the rotations of GS have the same sign in determinant of A. And obviously, if you have different cycle, and if you have different GSs with different variables, they will not cancel out because they contain different variables. So that means that determinant of A will be just the sum of some sign. Then another sign of not the permutation, but the matrix itself. GS, and then the monomial corresponding to GS, and these will only contain cycles of even size. But what can we do with the cycle of even size? So if we have a subgraph of G, which is a cycle, which is a collection of cycles of even size, then we can just, take every second edge and get a perfect matching. Now you may wonder perhaps what happens if a perfect matching is unique. Would we be able to detect it? So that's actually what the other proof is about. So if we have a perfect matching, so the perfect matching implies determinant of A is non-zero, well, then we can just consider this perfect matching on this our directed graph G prime, G star on G star. And then we have it, and we consider it cloned with itself, so something like this. So if we had some perfect matching, I don't know, 1 to 5, 3 to 7, 2 to 4, and 1 to 3, 4, 5, and 6 to 8. This would be a valid subgraph GS, which only contains even cycles. That means this one will be in the determinant. And actually it won't even have a reciprocal in a sense, because if you flip any cycle, you get the same cycle. So this one for sure will not cancel out with anything else. And actually the corresponding term in the determinant would in this case be x15 squared times x, again, some sign, x37 squared, x24 squared, x68 squared. And it will contain a lot of our stuff. So we have shown that essentially we have proven the theorem that if there is a perfect matching, this perfect matching will be as a monomial in the determinant. And if the determinant is non-empty, then all it contains are these cycles of even, this collection of cycles of even size, which correspond to monomials. And these collections of size, we can either split in, two matchings or more matchings, depending on which one we take. So this was this step.
Okay, so if the proof is finished, it's a good time to raise the hand for people who think they understand the proof. Are there any?
How to raise
Yeah.
reaction. It's a reaction.
Yeah. It's even better way to raise the hand without using Zoom. Okay.
I understood, but I don't find the button to raise the hand. So
Okay. You can just raise a hand physically. If you can find your hand, you can do it. Okay, maybe there are some questions then from people who did not raise the hand. Maybe there are questions. No, there is a kind. Okay, there is a kind of strange thing in this proof, but it seems that that's true. That if the polynomial is not zero, then it contains some term which consists of squares of all of squares of variables with coefficients 1. Is it true? So if the determinant of this matrix is not zero, then it includes a term of this form, which somehow is not immediately obvious. But it seems that it follows from the proof. Do you understand it correctly or not?
Coefficient may be -1.
Yeah. Coefficient. Yeah, depending on the number of the whether
Exactly.
n is multiple or 2 or 4. Yeah. But it's strange, but okay.
Yeah, I mean, it will contain this term because, again, if we just said if a determinant is non-zero, then it means that the graph has a perfect matching, and a graph having a perfect matching means there is this subgraph which only contains this. But this is per construction. We constructed the Tut's matrix in a way that it works like this. Obviously, this is also true for general skew-symmetric matrices, because every skew-symmetric matrix is an instance of a Tut's matrix. So you get some bonus algebraic properties about matrices.
Yeah.
Yeah, so if we are done with this proof, we will move forward to a more recent and a more important result.
Yeah, but by the way, from my student years, I remember that there was something which is called in Russian prufyan. and and it's something like this, or it's I'm completely mixing things. No,
Yeah.
if no one knows what is Pfeffian, okay, then
Pfeffian is a square root of determinant.
but it's not for skew-symmetric matrices.
Oh, you mean Pfeffian? Maybe.
Pfeffian, yeah, but in
Yeah,
Russian it's Pfeffian.
it is for skew-symmetric matrices, but it is a square root of this.
And it's a
determinant.
polynomial.
No,
Yeah.
no, I mean, Pfeffian is
So
a bit different.
So there is another statement that this determinant is a
exact
square of
yeah.
some polynomial.
Yeah.
Wow, but why? Is it something which can be explained, or it's
Yeah. So
result?
you can again, it's a square. You can explain it, but I think again a formal proof would take a bit too long. But the idea is that every of these monomials correspond to a collection of cycles. Every collection of cycles is a combination of two matchings. So actually, what this determinant is, it's a sum of all matchings squared.
So what is Pfeffian then? If you take this Pfeffian or Pfeffian,
now, the Pfeffian is
polynomial,
an extension of Tutt's matrix.
in terms of graph.
Pfeffian is a sum over all matchings, but with signs. And signs should be defined in slightly peculiar way in these elementary combinatorial settings, but it can be defined.
Okay, it's in.
Do you need the exact rule?
No, I don't want to interfere with other things, but in fact, at some point, if you can explain it, it will be very interesting. Okay, but let's move for now.
I have explained it some years ago.
Yeah, sure.
You can read my explanation.
But still, okay.
Yeah, I mean, we won't need Pfeffians for the rest, but you do need Pfeffians in context of matchings for planar graphs with exactly the same incentive. But we won't discuss that because we will discuss a much bigger result. So then we move to derandomization. So everything what we just did was randomized, and it requires a lot of randomization in some sense, meaning it's not so easy to de-randomize in a standard way. So what do we do, and why would we do it? So first we recap what the NC is. So the NC is the complexity class in the complexity theory, which is the class of problems solvable on polynomial number of threads with logarithmic depths, meaning if I give you arbitrarily polynomially many computers and each of them is only allowed to compute log n steps, can you solve this problem or not? Now, the algebraic algorithms are important.
No, but what you try to define is a non-uniform class or uniform class. No, maybe it's not needed, the exact definition is not needed, but just if you want us to understand it exactly, just what do
well, they don't have to be universal, so they can do different.
Okay,
they can operate.
Okay, let's skip it for now.
I mean, there are models of parallel computation, but this one is in a classical one, where you cannot access memory at the same time.
No, but it's uniform class, so it's a class of circuits or a class of how do you define it? Or some model, or how do you define
the
it?
NC class, you mean?
NC, yeah.
There's a class of algorithmic problems.
Okay, but it determines in terms of circuits or not?
No, I mean, just like P is defined, there's really not, I mean, you can define it, I guess, either way, but it's the same as, there's not much difference to P in the sense how it's defined, except that we define computation differently.
Sasha, it's uniform.
But what does it mean then? That we can generate in polynomial time the circuits of logarithmic depth?
Right.
Okay.
Okay. And as we have just shown that perfect matchings are in RNC, the randomized NC. The NC stands for next class, but it doesn't have a meaning beyond that.
But why the computation of determinant is an NC?
Now this is a linear algebra question, but I think there is an algorithm which can do it in log n depth by considering the sum matrices.
Strange because somehow the Gaussian elimination is not logarithmic depth, or and if we compute it in usual formula, it's not polynomial size. So how do we combine these things?
I mean, I'm not an expert on modern determinant computation.
No. Just no. If anyone now knows this, maybe
I don't.
anyone knows why the determinant is an NC. No, we can continue.
I have known it 2 weeks ago, but actually I forget now.
Okay, no. 2 weeks. 2 weeks is quite recent. So maybe
I think with minorand it doesn't work like NC2 you get. But like you take you take a row and then every element of the row, and then you take the determinant by dropping the row and the column of this element with some sign.
But if you do it recursively, then you just get the normal sum for all permutations. So it's
I'm stupid.
not polynomial size.
It doesn't work. Sorry.
Okay, only one of us knew this, and even Misha has forgotten. Okay,
I not completely forgot, Sasha, but I'm not ready to explain you in your style without formulas and without any time for thinking about the question.
Okay.
But I can say that you need, say, Newton identities in the construction. You should compute actually traces of yes, you should compute powers of matrices and compute traces. Traces is the sum of degrees of eigenvalues, and this symmetric function can be expressed via elementary symmetric function by Newton identities. And all this thing can be done in NC, but it requires some consideration because there is some technical details.
And it can be done in arbitrary field. You don't need to be algebraically closed.
If you have circuits with addition and multiplication, then yes.
There are no complex constants. I don't know. Okay. Let's stop here for now. So how do we do?
So they are in RNC, but obviously, since the normal matching algorithms, which you have seen, which probably all of you know, like with augmenting paths and stuff like that, they are not parallelizable, or at least we don't know how to parallelize them. That means we cannot put it in NC straight away. So the question is, can we remove a randomization but preserve parallelism, at least for bipartite graphs, which is already, it's been an unsolved problem for over 60 years. Now you could think of a practical motivation for this problem by saying, so what if one day a meteorite would come to hit the Earth, and we have only limited time, so we need to distribute all people according to like the actions that they need to take to stop the meteorite from falling, and we have like 7 billion people and maybe 7 billion actions that we need to take. And obviously we need a perfect matching, so everyone does something. And because it's a very important topic, we don't want to rely on randomization, because if it fails, we don't want it to fail. So, and we cannot compute it without parallelism, because 7 billion is way too large number. So then we could take all the computers on Earth and run the algorithm that I present now. And we would get an answer whether we can do it or not, and how do we do it.
Yeah. Really practical motivation. Okay, let's.
The best I could think of. I tried to find better ones. So we start with a simple case where we assume that we have a weighted bipartite graph, G, and the minimum weight perfect matching is unique. That means we have weights assigned to each edge, and the minimum weight perfect matching is unique. So instead of bipartite adjacency matrix, we have a weighted bipartite adjacency matrix where we put 2 to the power of a weight in the matrix. So here you can see the bipartite graph and the corresponding bipartite weighted adjacency matrix. So what do we know? We already know about the determinant of this matrix, that the determinant corresponds to...
So now we don't have variables, we have just integers.
Yes, we have just integers.
Yeah.
So we can compute the determinant, and we know that the determinant will be a huge sum, and every monomial in this sum, it will correspond to a perfect matching of some weight. Because we are bipartite, we don't need to think about these cycles. It's just a permutation. And moreover, we know that the determinant divides the weight of the minimum weight perfect matching. Because since the minimum weight perfect matching is unique, all other matchings are at least 2 times, or all other monomials in the determinant will be at least 2 times, 4 times, 8 times larger than this minimum perfect matching. That means they can cancel each other out, maybe, but the minimum one for sure will not be cancelled. And since all the larger matchings have a larger weight, obviously the determinant will also divide the weight of a minimum weight perfect matching, and will be non-zero.
But now the numbers are rather big. They're exponential in the weights.
Yes, but you can still compute the determinant in polynomial time even with these numbers. I mean, the space is still polynomial, and the algorithms, there also exist algorithms which compute the determinant in parallel for such matrices with...
No, but even the answer can be long.
No, but the answer is 2 times, so the number of matchings, I mean, the determinant is obviously bounded by the size of the entries of a matrix. So since all matrix entries are polynomial in size, the size of a determinant will be also polynomial. I mean, if we assume the weights,
you mean that weights are given in unary somehow, yeah? Or because you don't say what are the weights. If they have n-bit weights, we have 2 to the n-bit determinant.
No, so okay, n-bit weights are obviously bad, but the weights are numbers which are polynomial in n. So if we have n vertices, the weights would be polynomial.
As numbers, not as strings. Yeah, as numbers.
Yeah. But yeah, I mean, you can think of them as unary as well. So.
Yeah, okay.
Them as input, but if we have a unique minimum weight perfect matching, then everything is nice. We don't need any randomization. We can just go ahead and compute the determinant in parallel. And not only do we verify whether this matching exists, we also get the weight of this matching. And moreover, this can be easily parallelized to find a minimum weight perfect matching. So we don't just want to verify its existence, but also find it in parallel by removing, since the matching is unique, you can just run the number of edges algorithms. Each of them computes the minimum weight perfect matching on a graph without an edge. And obviously those where the minimum weight of those where the determinant changes parity, we'll have this minimum weight perfect matching destroyed, and those.
But if you remove edges one by one, it means that depth is n.
No, in parallel. So you remove one edge from the original graph. On the second one, you remove another edge, and you do
yes, but depth. How you can remove several edges at one level of depth?
You never remove several edges. You remove at most one edge.
But then we need n layers of removal.
No. You never
look sequential.
So the idea is that you run this algorithm on the original graphs and m in the number of edges, copies of the original graph where each of them has one edge removed. So you don't go in depth, you just remove one edge and then you stop. So you run it m times. You never remove two edges.
We see whether the minimal weight changes.
Yes, because it's unique.
It's unique, so just we can find whether our edge belongs to the minimal weight matching, because if it belongs to the minimal weight permutation, then after its deletion, the minimal weight increases. Maybe permutation exists, but the minimal weight increases. And if it's not, then the minimal weight is the same.
Yes, but in this case, you don't remove edges one by one. You consider several.
No, not cases. One by one. Removing edges, one at.
You consider all edges removal at one layer, and then
yeah. Just one by one is confusing. You shouldn't.
Yeah, I didn't use the best expression. Yeah. So yeah, each edge is removed, but no, never two edges are removed.
Yeah, but it all assumes that the minimal weight is unique.
Yeah. So this is a nice assumption which we should just do. But under this assumption, we can solve it very easily, as you can see. No randomization required. Easy polynomial time algorithm, and not only can you verify the existence, you can also find this matching in NC. Now, if it wouldn't be unique, already finding it would become harder, and also we get other problems. So what do? We consider, now this will become a bit more technical, so we consider the graph GM, which now we consider a case where the perfect matching is no longer unique. And we consider the graph GM, which is the union of all minimum weight perfect matchings with weights removed. So if we have a graph and it has many minimum weight perfect matchings, each edge, which is at least in one minimum weight perfect matching, goes into GM.
So we consider it purely theoretically. We don't know how to find it.
Yeah, we don't know.
Just we consider. So first we start with some weights, arbitrary or some special, and then for these weights we consider all the minimal weight perfect matching, and then we let them remain in the graph.
Exactly. So we don't know this graph. We don't know how it looks. We just call it.
No, still, the new graph has some other matchings, but at least it contains all minimum weight perfect matchings. Yeah.
Exactly. And now we will prove a small lemma which says that every cycle in GM corresponds to a circulation of weight 0 in G, where circulation is a weight difference of an even length cycle. Now I will prove this lemma shortly.
No, but you should explain the lemma. So every cycle, what does it mean? So we take graph G. So what is circulation of weight? It's not clear.
So yeah, I will define it when we'll prove it just in a second. So for now, we can treat circulation as a bit of an abstract term, with the idea that if this lemma is true, and we remove all zero weight circulations from GM, then GM contains at most one perfect matching, because this lemma says that the cycles correspond to circulations. So if we don't have circulations, we don't have cycles in GM. And if we don't say cycles in GM, it contains only one perfect matching, because a combination of at least two different matchings will always create some sort of cycle. As we have seen, it will be actually a graph of many even cycles if you combine arbitrary two perfect matchings. So with that in mind, again, we will come to the motivation later. We want to prove this lemma.
Maybe you can state it still first. What just explain what it says.
So okay, I will draw this. So I will explain it in a second. So the idea is we have our original graph G, which has some weights. Say we 1, 2, 3, 4. And let's say that the weight of W2, so we have two, let's assume that W1 plus W3 is the same as W2 plus W4. That means we have two perfect matchings in this graph. That means that GM will look like this. And GM contains one cycle, which is this cycle. And now the circulation of this cycle, let's call it 1, 2, 3, 4. Of 1, 2, 3, 4. Is starting from a smallest vertex, but this is not so important, is the sum of even weight wedges minus the sum of all weight wedges. So it would be something like W1 minus W2 plus W3 minus W4. And you could define circulations only for even-sized cycles. So it's the sum of one half of the edges at even spots minus the sum of all edges at the even spots. And the lemma says, well, if you have at least every cycle here corresponds to circulation in here. Where again, this is the union all mean weight perfect matchings. So now maybe let's state something more obvious. So if you take two perfect matchings, right? Let's say we have two perfect matching, which is 1. This in a different graph, two weighted minimum weight perfect matchings. This is like M2. This is weight 2, weight 4, weight 6, weight 8. And we have some averages. And we have that weight of F2 of M2 is the same as weight of M1, where M1 is the black matching and M2 is the red matching. Then obviously it is very clear that the sum of this that the circulations of, like, let's say cycle 1 and cycle 2 is 0, because the weights of the matchings are the same and they all cancel each other out. If we consider that the black matching is always a positive under circulation and the other one is negative. Now what we want to say is a bit stronger statement, which says that every cycle here will be 0. So not just the sum of cycles, but every cycle will be 0. So how do we prove it? Well, the proof is actually very simple. So let's assume it is not 0. Without loss of generality, let it be positive. So that it's some constant C. And we have that W1 minus W2 plus W3 minus W4 is C. That means that the black one, the black matching, is slightly heavier on this cycle than the red matching. And all other obviously on all other cycles, you also have some constants. So now what you do with each cycle, you choose the less heavier cycle, less heavier matching on each cycle. So here we will choose red as the less heavier matching. And we do it with all the circulations. And we get some matching M prime, which is strictly smaller than the M black. Because it is on the cycle 1, M prime is weight of M prime under cycle 1 is smaller than weight of M, and at all other cycles it is at least as
Excuse me, can you please remind what is the statement of the lemma we are proving?
So the statement of the lemma is essentially that the cycles in the matching graph correspond to circulations of weight 0. And the cycles in the matching graph are combinations of perfect matchings. That means that if essentially what it says, if we take two perfect matchings, combine them together, they form a collection of cycles. Every cycle in this collection will have a weight 0 under the circulation weight. So difference between weights of odd and even edges will be 0. And we just said why it's 0, because we said, okay, let's say it's not 0. Well, then we just take the other edges on the cycle, the less heavier ones, and we get a matching M prime, which is strictly less heavier than the other matching, which contradicts to the fact that all matchings in GM are minimal matchings, minimal weight matching, perfect matchings.
Okay, so is there anyone who understands the proof of the lemma? Please raise the hands. Are there some people who understand the proof?
I don't even understand the statement.
This will be my second question, but maybe if someone understands the proof, and then...
But it's impossible to understand the proof without understanding.
Okay, so who understands the statement then? Who can explain the statement?
I understand that in the statement we have some assumption. What is our assumption? That the minimal weight a perfect matching is unique?
No. So the assumption...
I think we are completely lost all, as you see.
Okay.
So we
need a notion of circulation, and as I see, this notion is not well defined for audience.
No, it somehow should be clear from proof, but it isn't.
It is somewhat clear from the proof, but the exact definition is needed. Because we can twist arguments in many directions.
Okay, so maybe, circulation of a cycle C, where C is a cycle, I don't know, node 1, weight 1, to node 2, with weight 2, 3, so on, coming back to 1, is the, let's say, absolute value the alternating sum and difference of weights when we move along the cycle clockwise. So it would be W1 minus W2 plus W3 minus W4.
And the cycle is even.
Yeah, the cycle is even. Yeah. and then you come back to
So the cycle is even. And so it's a difference.
So you
between-
just define the circulation as the absolute value of this
Yeah.
So
alternating
it's a
sign.
difference between the weights of two matchings that can be found in the cycles. One, if there are two possible ways to make it a matching, to select the matching, and the difference is the circulation. Seems, yeah.
Okay, yeah, and as I understand, we have we are given any weighted graph. I mean,
Bipartite.
non-oriented graph with weights on edges, right?
bipartite.
Bipartite or not?
Bipartite.
Bipartite. Okay, bipartite with weights on edges. Now we construct another graph called GM. Okay. And now the lemma states something about circulations of cycles in GM. Every cycle in GM corresponds to circulation of weight 0 in G. No, the lemma states something about circulations in G and not in GM.
Can you explain again how we construct the GM graph from the original one?
Oh,
Yeah,
that's
so
I understood actually. GM is obtained as follows. We take all minimum weight matchings. For every minimum weight matching we consider all the edges, and then we just join them.
Yeah. So for example, if there is only one minimal weight matching, then GM is just this matching. But if we have several, then of course we have some kind of loops, because in GM we have different. If we have two matchings and combine them, we get sometimes they are different, and then they create
and we consider perfect matchings. I'm sorry, only perfect matching.
Yeah.
And now we are interested in cycles in GM, and somehow cycles corresponds to the matching in the original graph, as I understand. So when we have a cycle in GM, every cycle in GM is obtained by taking edges from different matchings. For example, we can use 3 matchings, and from their edges we can construct one cycle. Right?
Yeah. So it could be multiple.
So if we take a cycle in GM, then the edges from different matchings somehow should, if there are only 2 matchings, they probably they should just alternate. But if we have many matchings, then strange things could happen.
Okay, assume that we have 2 matchings and they are combined in a cycle. Why the circulation is 0?
So
if they have the same weight, it's quite obvious.
Because these 2 matchings have the same weight.
Yeah, but the difference between them can be made of several cycles, so it's not clear.
Why?
No, the matchings can differ in several parts of the graph, in different parts of the graph. And so in GM, we have 2 cycles here and there.
So, okay, so this is what I was showing here. So if it is several cycles, so if we have several cycles, the idea is if one matching is heavier than the other on a different cycle,
then we can, from these 2 cycles, we can construct a matching which has smaller weight. That's why it's impossible.
Yes.
So we know that the sum is 0.
Yes.
And that implies that we can decrease the weight of the perfect matching.
But actually, we have another problem. A cycle in GM can be combined from several minimal
So
matchings.
if we have
But
more
Misha,
than two minimal
Misha, I
matchings,
guess at least we have understood why it's true for cycles combined of two matchings, right?
It has been explained. Look at the picture.
No, I guess I understand this case at least.
Yeah.
but what if we have a cycle made of several matchings?
No, for example, 3. I don't understand that. Assume that we have 3 matchings.
So in case of a free matchings or like more matchings, the proof works exactly the same. I mean, the easiest argument would be, I mean, the same argument essentially, that these all cycles are even, right? So we have, I don't know, 3 matchings.
And
Let's take
each edge can belong to some specific matching. I don't know. We have not
For
3
example,
but 10 matching, but
left
all they are from
rectangle.
different matchings. So how do we deal with this then?
Right, so let's say we have
Gray,
different matchings.
blue. Mhm.
We have 4 matchings. And again, all of this cycle has a non-zero circulation, right? So this is circulation of 3 is NOC.
Yeah.
So the idea works exactly the same in the sense that now you consider all of these 4 matchings. So you consider the symmetric difference, or like the union of all of these 4 matchings, or like let's not bring in symmetric difference. Let's just consider the union of all of these symmetric matchings.
Yeah.
And the argument is exactly the same, that from these 4 matchings, you can construct a smaller matching by taking in each cycle the smallest circulation. Since we have, if we have, I don't know, D edges here.
Yeah, it seems that I understand. Yeah,
It's a deregular graph.
we just construct again a matching the smaller weight. Yeah.
But why can we do this?
Because it's a deregular graph.
You can choose in each cycle. You can choose the minimal.
So we consider
part.
all cycles of non-zero
all
circulation.
cycles formed by symmetric difference of this.
What?
Look, you have several matchings. They may intersect at some on some set of edges. We take this set of edges intact. All other edges form a collection of cycles, and we consider this collection of cycles.
No, I am lost. So we have several matchings.
Yes.
And they have some common edges.
Yeah, and common edges we don't.
But why the rest?
Touch.
If we just delete all the common edges, we don't have more. Why do we have anything?
I mean,
nice
common in all
after that?
4 or in all D matchings, I think.
But yes, we have a problem because it is possible that an edge is in 2 matchings and is out of 2 matchings also, something like this, and how to count it, it's not quite obvious.
No, so the probably the simplest argument is by saying, okay, if we have D matchings, so these are D edges, this is formed by D matchings. We can consider the graph which only contains these D matchings. This is a deregular graph because these are only perfect.
So we consider
matchings.
it with parallel edges. Yeah.
Yeah. So it's a multigraph. It can be a multigraph.
Yeah. We consider a graph with parallel edges. Yeah. So what?
It could be a multigraph, and it's a deregular graph. So what you do is in this one, right, in this cycle, you take the smaller weight one. Okay, so you take the smaller. So let's say that day 1 plus day 2 is smaller than day 3 plus day 4. Right?
Okay.
Now you remove those from the graph, and you do the same one. And now you find a different cycle in a different cycle. And these vertices you also remove from the graph. So the graph still stays regular. And now you find a different cycle. You again remove in the circulation, in the zero circulation, just take any edges. If a non-zero circulation, you take the smaller ones, and it always stays regular. And because it's regular, it will be always contain cycles.
But if we remove this with vertices, why the graph remains regular? I don't understand. Some parts far away do not change a degree, and
because it's a perfect matching. So by removing the vertices, because you only have perfect matchings in the graph, it stays regular.
No, what we remove these 4 vertices, yeah. And
yeah, so we've matched
the neighbors. The neighbors have now, some neighbors have now smaller degree.
Yeah, but this graph still has perfect matchings, right?
But in the other part of the graph, the degree is unchanged. Why do you say?
As I see, we delete not a cycle, but all edges of these matchings.
Yeah, you can do that too, I think. Let me figure.
No. What do you mean by 2? So if we just delete the cycle and all the vertices and these edges, and edges, then do you claim that we get the perfect, the regular graph or not? This I don't understand.
This is quite clear.
What is quite clear?
Then if you delete 4 matchings, say.
No, for matchings another story. But if we just delete these 4 vertices and all the neighbor edges,
no. As I understand, we should delete all edges of this.
So we cannot delete only just vertices and edges.
Yes.
But if we delete all of these perfect matchings, then there might be nothing left.
It's possible. Actually, I don't understand how to finish my initial optimism.
But if we delete only this just 4 vertices and edges, we lose regularity, I guess.
I thought we didn't,
but how it's possible? Because imagine there are thousand other vertices. Then some of them are not touched at all, so they keep the same degree d, while some neighbor vertices which has edges connected to this 4 will decrease their degree. How can you get? How can we hope to get the degree on the same everywhere? This is what I don't understand at all.
Okay, the argument comes from a sense that all of these vertices are from some perfect matching. So if you delete these, if you have a lot like the edges, each vertex.
So you're now explaining what? Say it again.
Why it stays regular if we delete.
But it cannot stay regular because we decrease the degree of some vertices, but still there are many vertices. So some of them do not change a degree. This I don't understand. How it can? It's not possible that it stays regular.
Okay, I think
maybe it stays regular, but not d prime regular, where d prime is changed.
Yeah, but the problem is that there are some vertices far away which are not connected with all of this, and this far away part of the graph will not be changed if we just delete 4 vertices. Maybe we should delete all cycles, or we do something else. I don't know. But if we just delete one cycle of length 4, of course we cannot keep the far away parts. Something should be modified here, I guess.
Yeah, that is right. Yeah, I think you need. I remember it wrong. So you should not keep the cycle. You should delete something else. But
yeah, okay, but maybe if you believe still that the lemma is true, now let's look on the lemma again and see.
Yeah, I can look up this last
Yeah,
detail.
yes,
I
but
mean,
let's look at the
the end
statement
of
of the lemma again. We can believe you for a while if we
Okay.
just. So you say that if there is a cycle in GM, so
Then
if we can get GM uses edges for all matchings. So imagine we have a cycle there.
Mhm.
Do we claim that this cycle has zero circulation? Just exactly.
Yes, we do claim that.
Or we claim that there are some other cycles that has weight zero, other circulation of weight zero. We just say that, or we claim that there's just this one has weight zero.
If we found a cycle which is in GM,
yeah,
it has to have a circulation of weight zero. If we just found a circulation of weight zero, it does not mean that we found a cycle in GM.
By the way, I'm confused now about the statement again. Do we claim here that every cycle in GM is even?
No, it
is
of course,
even
because
also.
because if it's bipartite, every cycle is even because the graph is bipartite.
Okay. I see.
Yeah, no, but if we have a circulation of weight zero, then by definition it's a cycle in GM, I guess.
No, it's not cycle in GM. Because GM is combination of unique minimum weight perfect matching. It's nothing to do with circulations by itself.
Oh, you say that the circulation is just in G, not in GM.
Yeah, GM is unweighted, so GM does not. So if you look at the definition,
but it's smaller graph. But you say that cycle in GM corresponds to some circulations of the entire graph, even with edges not included in GM.
No, to the same circulation. So we have a cycle, and if we look at the same cycle in G,
the same cycle becomes a circulation.
Yes,
but you don't claim anything in the other direction. If there is a circulation of weight zero in G,
it would not even be true in the other direction. It's a one direction. So if I found a cycle in GM, what I know is that this cycle came from some perfect matchings, unique minimum weight, and now to disprove that we might look again at the end.
So you say that if it has not weight zero, this means that something the odd things are not the same as even things, and this somehow should from that we somehow should conclude that there is a smaller weight match.
Yes. So again, I'll
somehow use this fact to optimize weights from one of our. Okay, but this is not obvious at all. But also there is no reason to believe it's false.
Yeah, I'll check at the end again after we're done.
Yeah, okay.
I have it written down in another document. I just need to open it.
Yeah, okay.
I have it. It's all right.
Yeah.
So, and from this we can conclude if there are no zero circulations corresponding to the cycles in GM, then GM contains no cycles, and thus G also and thus contains one perfect matching, and thus G also contains one perfect matching. So if we manage to remove all zero circulations, we manage to make GM a cyclic, and by making it a cyclic, we make the perfect matching unique.
No, but we don't know GM. We have G.
Yeah, we don't know it, but we just say, yeah, so this is
if we manage to remove, but we don't know from where to
we even don't know it, yeah. But this is the fun part about the group. We remove something from the graph we don't know anything about. And this is probably why it took so long to find it.
Okay.
So now a very important fact is that if GM has no weight zero circulation, meaning that there is some cycle in GM which would have a zero, there is no cycle in GM, that does not mean that the original graph doesn't have a zero circulation, which is what you asked before. So we might make GM acyclic, but the original graph still has 0 circulations.
Okay.
So now our goal is not to make the original graph circulation 0 circulation free, but only make this GM acyclic by removing all cycles from it.
Without knowing the GM.
Yeah, without knowing the GM. So for that, we will use a different lemma, which says that if we have some collection of cycles, and so this is a more technical result, if we have some collection of cycles in a graph G, then we can find weights of n squared times the size of this collection of cycles, such that one of these weight assignments will make all cycles have a non-zero circulation. So this has nothing to do with GM or G at the moment. Yes, we just look at some weighted graph.
No, C is a collection of cycles in some unweighted graph.
Some weighted
Just
graph.
No, but we don't have weights. We invent the weights.
Yeah, no, this lemma has nothing to do with, it's an abstract lemma. It has nothing to do with.
Okay, but you say that you consider weights assigning functions for G. So the original weights are not used. We just have a graph.
Yeah, okay, that is correct. In unweighted graph, sorry.
So
yeah,
we have a graph, and then we have a lot of weight assigning functions, such that all cycles have a non-zero circulations.
At least one of them will satisfy that all of
Yeah. So normally we can take just a random assignment, and this random assignment will make with probability 1 more or less will make no circulations, because it's just kind of a condition which is rare to.
Yes. So this can be all done randomized very nicely, but we're obviously de-randomizing, so we have to rely on
so we need instead kind of a random assignment with a small probability space, and still when then we can take all the functions from this thing.
Exactly. So what do? We prove this lemma by constructing this family, so it's a constructive proof. And the idea is as following: so we take T as n squared times S, where S is the cardinality of all these cycles. And now you consider the family F functions Fi, where Fi, so let's enumerate the edges. Let's enumerate edges in ES 1, 2, 2, 2, and we say that Fi of EJ, so if assigning function assigning the weight to EJ is 2 to the power of J mod I. Right? So we have for I from 1 to T. Maybe not 1. Maybe 2.
So this will be family. So this family will be indexed by just this i's.
Yes, very simple family in the sense that it just assigns the weights. It takes the exponential weight and just considers its modulo I. And the idea is that all circulations under this assignment, under some Fi will become non-zero, indeed.
So to compute the circulation, first we can compute it without modulo I, and then it will be non-zero, because it will be just combination of different edges.
Yes.
And then you say that each of them can have factors, but not many of them. So there should be some I, which is not the factor of any of these things.
Yeah.
So the question is the number of cycles. How many cycles, how many possible circulations, places for circulations you have. Yeah.
Yeah. So the idea is that we consider. I mean, we know that we have C cycles, right? S cycles per definition. And these are only the cycles where we care about the weights. All other cycles we don't care about. So what do? We consider the product of all of these circulations. So circulation for cycle I. So assume this wouldn't be true. So then
so
this
how
product,
many cycles do we have?
S.
No. This is S cycles, but we need now are interested how many potential circulations we have. Yeah.
S.
No, but this S cycles form a graph.
No. We only care about the circulations in these S cycles. We don't care if there are other circulations which are zero.
But I think we cared about circulation in a graph, which is a union of the cycles.
No. We only care about the circulations of these S cycles.
But why? We before needed the union of the cycles.
No, we only want to remove these. We target these specific S cycles and we make them non-zero. There may be some other cycles also intersecting with this
But
cycle.
why then? I don't understand. Just say it again. Show again the statement of the lemma.
Okay, so the statement, maybe I haven't written it such that all cycles in C. I should have.
Oh, just cycles in C.
Yeah. I need to edit this afterwards.
Yeah.
So all cycles in C have a non-zero circulation. So we don't care about all cycles in G or all cycles in the union of C, just these C cycles.
Yeah.
So it's a very weak statement in the sense that we just need to remove these S cycles. So what do is we consider the product of these circulations, and since there will always be zero, so we claim that where there will be always a zero circulation, we know that this product mod j is zero for all j element of 1 to t. Yeah.
Yeah.
So proof by contradiction, proof by contradiction.
No, modulo I. No, you some change the notation.
Yeah, okay, so circulation, let's say circulation K.
You take it modulo I.
Yeah.
Yeah, it's rather strange why you don't take the prime numbers, then it will be easier.
I mean, it doesn't matter, but you can also take it with the primes. And the idea is that, okay, so what is this product of circulations? These are these 2 to the power weights. So we have that this is 2 to the power.
Why do we have product of circulations? It's just I think we have 2 to the sum W minus. Why do we get the product?
Because if one circulation is 0, if it's just one circulation is 0, the whole product becomes 0. So this is why we consider the product. Because we want to ensure that all circulations are non-zero. And if at least one is 0, for each weight assignment, some other circulation can become 0. So we're just saying that the product.
No, when you say circulations, you just take weights 2 to the WI or WI.
Yeah, just take these weights. So I mean, this obviously is the product of circulations under Fi, right? So we assigned fi each weight, and we compute the product of circulations modulo I, and this is the same as saying that.
Yeah. So, Kolya, do you understand what is happening? Maybe you can explain me, because I'm lost now. Somehow, it's.
We want to prove the lemma.
And what the lemma says? Say it again.
The lemma states that if we have a small number of cycles, s cycles, and if we consider these weight functions, then there is one of them which for which the circulations of all cycles is non-zero, right?
But do we take powers of 2, or we just take the weights as they are?
And the weights as
we do not have any weight, given weight. We assign by this formula. As the power of all weights are powers.
The power of J.
Modulo I for ith.
Yeah, so we want all of them be non-zero.
Yes, and all of them are non-zero if and only if their product is non-zero, right?
Yeah.
And the product is non-zero if and only if their product without modulo I is non-zero. Modulo I guess. We multiply.
So each without modulo I, the circulation is not zero. So modulo I, it's non-zero for most of the i's. And so if there are not too many cycles, there are still some i's for which all of them are zero, just union bound. Yeah. But you can say in the terms of product, but it's just union bound.
We just want to ensure that this product is small, as I understand, or small, right?
Yeah, because each of the thing is small. Yeah.
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 It's actually exactly. So I think if it's even simpler if we take the powers to the power of m and not to the m, and assign it to e yot as going from vertex yot. So the weight of the edge is 2 to the power of number of its smallest of its largest vertex. Or the sum of its vertices.
Okay, let's not go in this, because if it's okay, then it's no. You somehow need to know the number of prime numbers between 2 and t somehow.
Yes. So yeah, there's a theorem. So we can say that this product, without the mod, because it's obviously non-zero, it's at most 2 to the m. S plus some plus, so every circulation has a size of at most n, so this is at most n to the power 2 ms, because the maximum weight of a circulation is n times 2 to the power of m, and so we say that it should be mod I equals 0 for all I in 2 to the power of t, but this is substantially smaller than due to the prime number theorem. So this is smaller than the least common multiple of 2 to the t, where t is defined as n squared s, which is a theorem.
Yeah.
Because m is bounded by n squared, so the result is the same.
Yeah.
So what we're saying is that n times 2 to the power of m squared times 2 to the power of s is smaller as least common multiple of 2 to the t n squared s. And I mean, you actually do with some constant, so you need a constant here. So that's why we also say that t is element in the O notation n squared, because this term is actually n to the power of s times 2 to the power of n to s squared, and this term is much larger. I forgot the exact bound, but this would be something of would have to at least a log n log n and log n and squared s.
Okay, we cannot follow it anyway, but so I understand that it's just you
Assume the lemma.
Sorry?
Assume the lemma is
yeah.
true.
So imagine the lemma is true. So what do we do then?
No, but I mean, it's clear why it's true, because this expression goes much faster than this expression.
Okay, no. It's difficult to follow exactly, but okay, let's assume the lemma. You know, this is more or less clear what you are doing, and let's believe that it's what you want. You get what you want in this way. Okay. So how we use the lemma? Just say it.
So then we need another lemma, actually, and this is sorry.
No, it just no. Maybe we should just then switch. Stop now for today, because it's already.
No, we're almost done, actually. So the other lemma is relatively simple, and it just says if a graph has no cycles of length smaller equals r, it has at most n choose 4 cycles of length smaller equals to r. And the proof is simple in the sense, okay, assume you have a cycle of size 2r, and consider the midpoints. Oops, sorry, I didn't switch. And consider the midpoints of this cycle. So you have 0 to r divided over 2. So you have r, and then you have 3r divided over 2. And
in each part, the path is unique. Otherwise, we get a cycle. So you could construct. So in each part, the path is unique. Otherwise, you get a short cycle. So you can construct the cycle looking at these 4 points.
Yes. So no other big cycle. So this is a cycle of 2r. So no other big cycle of size 2r is allowed to go through these points, through any of these points, through any.
Yeah. So we can
through all of 4 of these points.
The unique path between.
Yeah. So actually, yeah. So you have n choose 4 cycles, because you are not allowed to use the same nodes in some other cycle.
Yeah.
Afterwards. That is clear. I mean, again, it can be made more formal, but the idea is the same, because you've got the midpoints, and if you have this cycle, which is also size 2r, and it goes through these points somewhere else, it will have some short path connecting 2 of them, so at least one of them will be smaller than r over 2, and this will be r over 2. We don't know which one, but at least one of them will be smaller, so we will get a cycle of size smaller equals r. That means 4 midpoints uniquely.
Yeah.
So we're not allowed to use these nodes with these 4 points in the other cycle, so we have at most n choose 4 of these cycles.
Yeah.
Because each cycle removes 4 nodes, and so on and so forth. Okay, so this lemma is clear, the proof also hopefully clear. And now the idea is to make it constructively. So we start with removing. So if we removed all weight 0 circulations of length smaller equals r, then we only need to remove at most n to the power of 4 circulations of weight smaller equals 2r from some.
But what do you mean by removing?
Assigning weights such that these circulations become non-zero.
Yeah, but if we assign some weights, we then we want to remove some other circulations, and then we should choose another weight, and so we get our previous weights are not used, or what? How?
Exactly. So how do we do it? So we start with the original graph and the matching graph with all weights assigned to 1. Then we remove all 0 circulations of length smaller equals 4 using this weights lemma by assigning n squared and choose 4 weights to G from this family of weights that we considered earlier, and we get some new graph G1, which now has probably less minimum weight perfect matchings, which are captured in the graph G1M. Now, this G1M again is the graph containing the edges of all minimum weight perfect matchings from G1, where G1 is this G with changed weights. So now we know that
G1 we don't know.
G1 we don't know, so we compute all in parallel because we assign all these family weights from this family function. Then we know that G1M, there exists at least one assignment which removes all of these cycles of size 4 from G1. So G1M will contain at most n choose 4 cycles of length smaller or equals 8 by the previous lemma, because G18, remember, is an unweighted graph, and it's an unweighted graph which doesn't have any cycles of size 4, because we removed all cycles of circulations of size 4 from G1, so G1M does not contain them either. Then we again take this family of functions, now on G1, and we again assign this family of functions to the, again, we don't know which cycles we are removing, we don't know from which graph we are removing the cycles. So what we do is, again, we assign all of these families, and you know that one of these families will definitely remove this bad collection of cycles of size 8 present in G1M. We don't know how G1M looks, and we don't know which cycles are in there, but we know one of these weight assigning functions will remove all cycles of size 8 from G1M just because there are so few cycles in G1M. And to not contradict with the previous weight, we offset them by.
So what you say that you get finally you get an not a polynomial but quasi-polynomial family, and one of the functions removes all get things unique. That's what
exactly.
you're saying.
Exactly, and. Exactly. So this is written also in the notice, because we don't have an access to G1, GIM. We don't know which cycles are present in there. We just know we have to remove them, and we know that there are a few cycles in there. And we know if there are a few cycles, there exists some family which removes it. Again, we don't know which family because we don't know which cycles, so we can't check. But one of these families will definitely do it. And then you continue going up and up and up. And at some point, when you reach cycles of size n, you're obviously done because there are no larger cycles than size n. And one of these weight assigning functions has made the perfect matching unique, given that there was a perfect matching, by removing all 0 circulations present in the original GM. So we got some GNM. And again, we don't know it still. We don't know which one removed it, but we know that there was one which removed it. And we only used pseudo-polynomial many weight families, and each weight family has pseudo-polynomially large weights, because every time we have to offset the weights by a larger power to them not interleave with each other. So this doesn't, the fun fact is, this doesn't mean that now the graph G, where we assigned all these weights, does not have any 0 circulations, but we know that all the bad 0 circulations that were needed to be removed were removed. because there were so few of these bad zero circulations. So even under this assignment, the G may have 0 cycles, but the matching graph will only have 1 matching because all the matching circulations were removed. So what are the, so yeah, again, to restate, we need n pseudo-polynomial number of weight families, we each having weights of pseudo-polynomial size, which shows that bipartite perfect matchings are in quasi-NC. Moreover, this algorithm, although very elegant, is still complicated. There exists about a 50-page extension to general graphs, so where with the Tuts matrices and everything, which does similar idea, but even more complicated. Now there also exists for planar graphs a polynomial time algorithm, so without this large weight families, and it relies on the Pfeffian, which you mentioned before. And it's still unknown to this day whether matchings are in NC or not, because this algorithm is the best we have. Yeah, so that's the consequences.
Yeah.
And yeah, so here are the relevant papers for to the ones. So for planar graphs, for bipartite one, and the generalization.
So
and
this is more or less what was what you
yeah, so I explained the second one and the third one essentially. So this is the Tuts matrix and the bipartite one. We didn't cover the planar one, and we didn't cover the general graphs because both of them are much.
Yeah. It's okay. Now I don't know whether anyone can follow completely. I definitely I'm not this person, but at least some kind of flavor what you can do and how you can do it, we get. But and this is already a good thing to do.
Yeah. And it's also very nice in the sense that you don't know anything about what you're doing and what you're removing, but you know that if you do it sufficiently many times, it doesn't matter what it was, you have removed it. So
yeah. Okay. Okay. So thanks a lot. Okay, we are a bit exhausted and confused, but that's unavoidable. Yeah.
Yeah.
Okay.
That's
so
why I did the presentation.
Next time probably we'll have Kolya speaking, trying to streamline one of the previous talks about this cat and ant story, but it depends whether the people can come. And also there is an interesting combinatorial question which comes out of Andrei Ramashchenko and other people work on communication complexity, but I would like to ask it, but today it's too late, so let's postpone it to the next time at least. Okay, so some people already left, but anyway, thank you again.
Yes, thank you.
Yeah, Bruno, don't you want to give a talk sometime, by the way?
Yes, but December is like the first half of the academic year is difficult, but but if you insist, yes.
No. Okay, no pressure. You can make it in January or in February.
Yeah, and I can speak about connectors and online matching, and maybe I will have new results by then.
Yeah, this is a threat. Okay. Maybe
no,
then
I mean, but I already spoke twice, so I mean,
okay.
Some people heard it already twice, so I need to have some new results.
You can hear it a few times without getting clear. Okay.
Bye.
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 Thanks.